So you walk out of your Cambridge IGCSE 0478 computer science exam feeling pretty great, right? You memorized literally every definition. Your teacher, totally proud of the effort. But then, weeks later, results day hits, and boom, you've dropped an entire grade boundary. What happened? Well, it's because there is this massive, dangerous gap between what you think teachers want, which is usually just recalling facts, and what Cambridge examiners actually reward. Today, in this explainer, we're adopting the examiner's mindset. Zero fluff, we're getting right into the exact strategy to secure top-band marks on one of the most notoriously mishandled topics out there, error checking with parity.
Most students write something along the lines of, parity checking uses an extra bit to find errors. Then they sit back, totally expecting full marks, because hey, it's true, right? But here is the really harsh reality. The examiner scores that a flat 0. The feedback is absolutely ruthless, usually saying something like, lacks context and technical sequence. This is exactly how you risk your grade boundary in an instant. The examiner just doesn't want a dictionary definition from you. They are hunting for applied reasoning.
Okay, let's dive into this. Why does ordinary revision completely fail you in the 0478 exam? Honestly, it's because traditional studying just trains you to recognize isolated facts. You know the drill. You build flashcards, you memorize these generic definitions, and then you just stop. But the exam demands comparison. It demands application. When you just recite textbook facts, you fall into these classic traps. You mix up validation with verification or memory with storage. But the absolute most fatal mistake, failing to anchor your answer to the specific digital scenario they gave you in the question. Look, don't just take my word for it. Listen to this principal examiner warning straight from the source. Generic responses rarely gain full marks. Answers must stay inside the given context. Think about that. If the exam question is asking about a school network, an industrial robot, or maybe an embedded system, your answer has to live and breathe inside that specific context. Writing out absolutely everything you know about parity without any direction, it's like handing the examiner a map of the entire world when they literally just asked for directions to the local store. And this brilliantly illustrates the next major hurdle. Just naming the method, like simply writing "use a parity bit," is a classic wrong turn. The source material is super clear on this. The marks, the real method marks, are hidden in how you explain the technical process sequentially. The examiner really wants to see the actual gears turning in your head, not just a slapped-on label. So how do we actually fix this? Well, in just a moment, I'm going to reveal a very specific examiner clue. It's this hidden signal that completely changes how you should write your parity check answer. And honestly, it is the absolute secret to unlocking those top-bound marks. But first, you need the framework that makes that hidden clue totally obvious. You need a system. So the crucial point is this 4-step high-mark framework. Think of it as your ultra-reliable memory structure. Whenever you're studying a concept like parity, you need to force yourself to answer these 4 prompts out loud. Number 1, what is it? Number 2, how does it work sequentially? Number 3, where is it used in the real world? And number 4, why is it better or worse than an alternative? If you can confidently answer those 4 questions, you have officially shifted from being a passive memorizer to a highly active exam strategist. Let's quickly knock out step 1 of our framework right now. What is it? Well, error checking with parity is simply a method to detect errors during data transmission. It works by appending one single extra bit to a string of binary data. The whole goal here is to ensure that the total number of 1 bits in that sequence is either an even number or an odd number. And that just depends on the protocol agreed upon by the sender and the receiver. Seems simple enough, right? But let's move on to the actual mechanics. This brings us to step 2. How does it work? Imagine we're tracing a sequence of bits, 1, 0, 1, 1, 0, 0, 1. If you count the ones in that string, you get 4. Now 4 is an even number. So if our system happens to use even parity, the sender just appends a 0 as the parity bit, simply because we already have an even number of ones. But if the system uses odd parity, the sender has to append a 1. Adding that extra 1 brings our total count of ones up to 5, which is, of course, an odd number. By actually walking through this binary manipulation, you aren't just reciting abstract theory anymore. You are demonstrating the exact technical sequence the examiner is hunting for. Moving to step 3. Where is it used? Real-world transfer matters immensely in the 0478 syllabus. Parity checking isn't just some abstract theory sitting in a textbook. It is happening right now in school networks, industrial control systems, robotics, secure communications, and embedded systems. When you connect your explanation back to these very specific Cambridge-style scenarios, all that dry terminology suddenly becomes meaningful. You're showing the examiner you actually understand the practical, real-world consequences of the technology. Okay, let's put this to the test with an interactive challenge. Imagine you are sitting right there in the exam hall, the clock is ticking, and this is your prompt. A robotic system transmits an 8-bit command using odd parity. Explain the error checking process. I want you to mentally pause this explainer for a second. Seriously, how would you structure your answer? What are the key steps? Predict exactly what the examiner wants to see. All right, time's up. Did your answer look something like this? The robot uses an odd parity bit. It counts the ones and checks if an error happened during transmission. Man, the classic flawed student answer. I see this all the time. It sounds kind of related, sure, but it completely misses absolutely all of the vital process steps. I mean, who exactly is counting? The sender? The receiver? What actually happens if an error is detected? Using vague wording like this completely destroys your chance for top marks. Now let's look at a top band answer. It would sound more like this. The sender counts ones in the 7-bit command. It then appends a 1 or 0 to ensure an odd total. The robot receiver then recounts the ones. If the total is even, an error is detected and retransmission is requested. Do you notice the difference there? We have a crystal clear sender to receiver sequence. We explicitly state the goal of getting an odd total. We mention the receiver doing a recount. And, critically, we state the practical consequence. An error is detected and retransmission is requested. That right there is exactly how you secure maximum marks. Now, what's really interesting about this is this brings us right back to that promise I made earlier. How do you actually spot the examiner clue? It's all about a disciplined 3-step diagnosis. First up, you have to identify the exact requirement. Does the task want a process explanation, binary math, or maybe a protocol definition? Second, classify the relevant data or hardware. Are we talking about a robot, a bank, or just a 7-bit string? And third, the ultimate clue, check if the prompt wants causes, effects, advantages, or an evaluation. If you diagnose the demand correctly, your answer practically writes itself. Let's escalate the difficulty a bit here. Listen to this sentence and try to spot the classic Cambridge wrong turn. The banking database uses verification to ensure the parity bit is correct. I mean, it sounds highly technical, doesn't it? Like a great answer. But to an examiner, that sentence is a glaring red flag. Let's move to a breakdown and see how this builds our understanding. Surprisingly, over half of students lose marks just because they mix these two terms up. The fatal error here is confusing verification with validation, or error checking. See, verification is all about checking that data entry matches the original source, like double entry typing your password twice to make sure it matches. Error checking, on the other hand, like parity, is about checking that data transmission is reasonable and intact after it's traveled across a network. Mixing these up is a fast track to lost marks. You absolutely must train comparison just as much as single topic explanation. To guarantee you never fall for these traps, you need to use the 3-pass revision cycle. Pass 1, secure your key definitions and, crucially, your contrasts, like knowing exactly why verification is not error checking. Pass 2, rehearse worked explanations and physically sketch out those binary parity diagrams until they are completely second nature to you. Pass 3, adapt. Change the scenario. Ask yourself, hey, how does my explanation change if this is a school network instead of an industrial robot? This layered style of thinking is your ultimate strategic roadmap. So, you've now mastered the mechanics and the strategy for error checking with parity. You know exactly how to structure the sequence and avoid all that generic fluff. But wait, what happens when vague wording ruins your hardware and software answers? Mastering parity is really just one piece of the puzzle. You need to know how to decode the rest of the paper. Examiner language decoded? Next.
Will your next exam answer be a generic guess or a precision strike? If you want to stop losing easy marks to vague wording, watching our next explainer on computer science examiner report mistakes is an absolute must. Click the explainer on your screen right now to uncover the remaining traps before exam day. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations.